Okay, so the motivation. So forecasters will typically issue severe weather watches 8 hours in advance. So this is typically, you know, the morning of, if it's an evening severe weather day. And then once the events really get going, they start issuing tornado warnings, sort of on the time scale about 30 minutes before the events happen. And this is really once the storms get going, they're issuing these warnings. So that sort of leaves a gap in the middle between this 8 hours and 30 minutes that we're looking to fill with the Warn-on-Forecast system. So what's the value in filling this gap exactly? Well, because these forecasters are making these warning decisions based off of real-time observations, they are essentially waiting for them to happen. And it would be nice to give these guys probabilistic guidance to help them anticipate what sort of severe weather hazards that may be happening later that evening. And also they're, you know, along with this probabilistic guidance would allow for longer lead time so people can make decisions earlier in advance of these severe weather hazards, which helps in, for example, hospitals taking preparations, because that can take on the order of an hour or longer to do. And also anytime that somebody makes a decision to prepare for severe weather, there's a cost in making that decision. So there's a value in providing this probabilistic guidance to the forecasters. Now, what is the Warn-on-Forecast system exactly? The nice definition I have here is it is a convection allowing ensemble aimed at forecasting severe weather probabilities at short lead times. Now, the specifics of this model are that it's nested in the hurry, and that provides the boundary conditions. The forecasts are 3-hour forecasts, and they're output every 5 minutes. And these forecast initialization times occur every 30 minutes from 1900 to 0300 UTC. And so this is about in the evening for where we live. This model is run at 3-kilometer horizontal grid spacing and has 51 vertical levels. And it also assimilates real observations made with the satellite, WSR-88D, and surface observations. And it does this through an ensemble Kalman filter. Now, the Warn-on-Forecast system, like I said, is an ensemble, so it's composed of all of these 18 different members. Now, there are 36 members in total, but 18 of them are unique, and they differ based off of their planetary boundary layer scheme and shortwave and long-wave radiation schemes. Now, there's been past work that shows that the radiation schemes show negligible differences for environmental forecasts, so I'm not really going to be focused on those in this study. But these planetary boundary layer schemes do make a difference, and the defining characteristic between the PBL schemes are whether they are local or non-local. And I'm going to go into what that means here in the next slide. The local schemes allow variables to be calculated at a given grid point using only adjacent grid points. Now, the vertical mixing in these schemes is driven typically by large eddies, which respond weakly to local variations in static stability. And I'll touch on that again in a moment. They typically have weaker mixing than the non-local schemes, and so this results a lot of times in smaller planetary boundary layer depths. And the two local schemes I'll be focused on in the study are the MYJ scheme and the MYNN scheme. Now, the other kind, the non-local scheme, allows variables to be calculated at a given grid point using more than just adjacent grid points. So, you know, they're using many grid points on either side. Now, because of this, they account better for counter gradient fluxes. So in a sense, hopefully they resolve more of the turbulent behavior that we see in the atmosphere. And because of that increased mixing, they typically forecast deeper planetary boundary layer depths. And the non-local scheme I'll be looking at today is the YSU scheme. Now, one thing I want to point out is these color bars that I put next to them are consistent throughout the talk. So whenever you see blue, that is YSU, magenta, MYJ, the orange, MYNN. Okay, I think I'm unmuted. So the Warn-on-Forecast system has been evaluated in the past and has been shown to create reasonable forecasts of hail, tornadic mesocyclones, and flash flooding events. And bulk verification methods, and this is when you're looking at like a lot of storms over a lot of cases, WoFS has been evaluated using an object-based method. we go. Now, the environmental forecast, so not storm scale like the past studies I just referenced, but the environmental verification has been done in the past with one particular study, and it looked at systematic impacts of PBL schemes. So that's going to be a particular study that's really important for the analysis I'm looking at today. This study showed that most of these schemes had cool, moist biases at the surface, and the YSU scheme had the smallest biases in environmental variables. However, it did exhibit a weaker storm response. And so this is going to be an interesting thing here because we're particularly looking at supercell environments, and there is going to be a relationship between the storm and the environment itself. And so we'll see how this YSU scheme does here. I want to touch a little bit on the storm environment modification because I'll be talking about that a lot in this talk. I'm breaking the general environment between far field, which is outside of 40 kilometers from the updraft of the supercell, and the near field, which is inside of 40 kilometers. Now, this near field environment is typically storm modified through things like low pressure perturbations that are generated by the storm that'll increase the inflow wind speeds. You could have something like anvil shading that it shades the surface and decreases insulation. And you also have mesoscale boundaries like gust fronts generated by downdrafts. And also you could have some cooling via precipitation into the inflow, things like this. So there's certainly this mechanism to look at here between the supercell and the environments. Also, the yellow representing the far field and the red representing the near field is consistent in the talk as well, so look out for those colors. The science questions that I'm going to look to address in this talk are how closely is WoFS representing the inflow environment, and we're going to do this through looking at wind speed and direction, temperature and humidity, also mixed layer CAPE, and 0 to 3 kilometer SRH. How accurate are WoFS storm scale predictions, and the main focus here in my study is storm location. How accurate is it actually resolving the storms in the right spot? And to what extent is WoFS predicting the storm modification that I just referenced on the previous slide? This has to do with timing and also distance from the storm. And can the ensemble mean be optimized by weighting the members? Right now, those 18 members are averaged evenly, and if some tend to be performing better than others, then perhaps there's some value in weighting those in the future. Now, the specific evaluation of WoFS that I'm doing, I'm obtaining the data that I worked on from the hazardous weather testbed that was conducted in the spring of 2019. And my choice on WoFS forecast to use I'm using the nearest WoFS initialization time and forecast time for all observations I'm looking at. So for instance, if I have an observation that happened at 2302, then I'm going to be comparing that to the 2230 initialization time valid at 2300. The particular observational platforms I'll be looking at is one, mobile radiosondes, and they give us information on environmental variables and thermodynamic and kinematic variables. Now, I put one location at one time here because whenever I'm going to compare the radiosonde observations in WoFS, I'm going to pick a specific forecast time to look at from one grid point. Now, the Doppler Lidar, which as far as I understand is a relatively new observational platform for evaluation of a model like this, which provides a time series of kinematic variables, wind speed and direction, which the time series aspect is the really cool part about that. We can see how WoFS does there. I'll be looking at 3 case studies from TORUS2019, May 17th, 20th, and the 23rd. Now, the TORUS field project, and on the right-hand side here, you can see sort of the general region that we were in during the spring of 2019. The blue, we never went outside of the blue region, but you can see that is a large area that we covered. And on the bottom here, you can see all the various vehicles that participated in this field mission, and there was actually some that weren't included in this photo. Now, the TORUS field project stands for Targeted Observations with Radars and UAS of Supercells, and that's uncrewed aerial systems, which you can actually see here on the left, the University of Colorado vehicles. And there were several organizations that teamed together for this mission. We had the University of Oklahoma, University of Nebraska, University of Colorado, Texas Tech, and NOAA all grouped together for this mission. And it was in the spring of 2019, May 15th through June 15th. Now, the objectives were to improve the conceptual model of supercell thunderstorms and also associating the composition of severe storms to the larger scale environment. Now, of all of these different observational platforms, I'll be looking particularly at mobile radiosondes, which were the Bisolate Radiosonde RS41 SGP, and they have temperature, pressure, and humidity sensors, and the wind and height variables are derived from velocity and location measurements using the GPS receiver. Now, to give you guys an idea of the different environments that these can be launched in, here's myself launching a weather balloon in the parking lot of the National Weather Center. Very calm, not very interesting. However, during TORUS, these supercell environments can be quite hectic. And this is my advisor, Elizabeth Smith, releasing a balloon. And this is actually one observation that I analyzed in one of my case studies. And this was later in the day on May 17th. And you can see all the different obstacles, us being on the road, power lines, trees in the way, very chaotic environment. The LiDAR data I'll be looking at was collected using the Halo Photonic Streamlight XR Doppler LiDAR, and it was mounted in the bed of a truck, which I have a photo of here in a moment. It collected PPI scans every 2 minutes, and it did this using a 7-degree elevation cone with 12 points in azimuth, and calculated the horizontal winds using a velocity azimuth display technique, VAD. And here we have a picture of the LiDAR in the back of the truck. This white box encloses the LiDAR, and we have a lid here that typically is on the LiDAR whenever we're not observing, but in this moment we were observing. So the lid is off and the LiDAR is collecting data. The processing that I did to the data was that for the environmental variables like CAPE and SRH, I pulled from a grid north and east and west of the observation. You can see here on the this graphic where the magenta dot represents the location of the observation relative to the storm, and the black dots represent the grid points that I'm pulling from to sort of create a distribution. The radiosonde travels through this area as it's collecting data, and so this is a way of collecting that, of dealing with that variability in location. And the Doppler LiDAR data was quality control with the signal to noise ratio filter, and I temporarily averaged that LiDAR data with a 6-minute window in order to get nice comparisons between the WoFS forecaster output every 5 minutes. Now, the radiosonde and the LiDAR data both collect data at a higher resolution, spatial resolution, than what WoFS exists at. So I had to spatially average the data using a 40-minute window in order to make that point-to-point comparison. Okay. So there's one aspect of this analysis that I wanted to pay special attention to, and this black dot here represents the location of one of radiosonde observation collected by the far-field sounding vehicle, which was the vehicle that I was in during TORUS. Now, all of these different little splotches here are the WoFS paintballs of 45 dBz reflectivity. You can see, number one, they roughly are in the same spot, but there is some variability in location, which means that for some storms, particularly these on the southwest side, the far field is in the inflow. But for these that are a bit faster, or at least placed a little bit more north to the northeast, these are, the far field vehicle may be in the outflow relative to these storms. And this causes a complication for this analysis. So if I were just to go into WoFS and pull the closest latitude and longitude to the observation, we end up with some issues that the errors in the environment can be influenced essentially based off of the storm location. If it's very cold and it should be warm, perhaps I'm in the outflow of one of these storms. And so this kind of confuses the analysis. And here I have a photograph that shows you that for some of these storms, I am appropriately in the inflow, and maybe comparing to this radiosonde observation, perhaps the comparison is nice and clean. However, these other storms I'm essentially sampling the outflow, and this is not something that I want to be doing. So the implication here is that we want inflow, and I'm going to do a storm relative analysis, which means I actually need to locate each of these individual storms in the Warn-on-Forecast system. And to give you guys an idea, is if there's 18 members, those are 18 storms I have to find for every time I want to compare an observation. So it turns out to be a lot of storms. So I used an object identification algorithm, the same that was used by Britt et al. 2020. Now I have a slide here to give you guys an idea of what the rough process of collecting the storm locations. First, the purple outline here is a 3-hour updraft helicity swath, and this is essentially giving you a feel for where any storms at all could have been in that 3-hour swath. Now, the blue pixels there are the WoFS UH object specific to the storm that I'm trying to look at. There might be in the vicinity, but it's the one that I'm particularly interested in that it corresponds to the supercell we were observing. The red dot here is the centroid of those pixels, which is calculated using that algorithm. And the red X here represents the real storm location. And so here, perhaps WoFS forecasts a storm that was a little bit to the north and west of the observation, or of the observed storm. Now I'm just going to click through these real quick just to give you guys a feel of these UH objects change shape and size as they move through. And this does add some variability, perhaps, to the location, maybe on the order of 10 kilometers or so. But it's not thought to be extremely impactful on the analysis. Now, sometimes those larger UH objects can break into smaller UH objects, and in that case, I went through myself and averaged them together to give a representative location for the centroid. And the nice thing about this is this actually allows me to calculate track errors. I can calculate the displacement between the WoFS storm location and the observed storm location. And I did that particularly during the longest deployment, or the longest LiDAR deployment of each case study, to give essentially a time series of how these track errors could be evolving. So now I'm getting into the case studies. The first case study is the May 17th case study. And this particular supercell generated several tornado reports from about 2230 to 0130 UTC, so several hours of tornadic activity. And also, I should mention, this was our first deployment of TORUS, and so it was quite a great first day for us. On the left here, I have a radar image of the target supercell just over McCook, Nebraska. And in the middle, I have the WoFS paintball. And again, these are the 45 dBz paintballs of all the different WoF members. Now, I'm going to overlay on top of those WoF members a black circle that shows essentially roughly where the real storm was located. And you can see that WoFS does a decent job of forecasting storms in that location, but there is some southeastern bias, about 15 kilometers in the storm location. And I included this video to give you guys an idea of the organized chaos of a field mission like this, where the yellow circle is the LiDAR, all the different dots and circles are other observational platforms. And this is a ground relative video here that shows the supercell essentially approaching the LiDAR, and all of our observational platforms hurrying to get into their respective locations to make their planned observations. And so this is just to give you guys the idea of the massive coordinated effort that this field mission really was. Now, in a storm relative sense, this image, we have panel A here and this image over here. This shows the storm relative locations of the observations that I'm going to be particularly looking at. So the numbers are the radiosonde locations, and the blue X's represent the storm relative location of the LiDAR. So keep in mind that the LiDAR is stationary and the storm is approaching the LiDAR. Now, for the first bit of analysis, I'm going to look at two radiosonde observations, the far field 2302 observation and the near field 0106 observation. So here I'm showing box plots of mixed layer CAPE, and these box plots were created based off of that grid that I showed in previous slides, and so that's how I'm creating these distributions, is pulling these CAPE values from all those different grid points. The yellow, again, is the far field, the red being the near field, and the gray means that the radiosonde actually didn't make it up high enough to calculate mixed layer CAPE, so these are the two radiosonde observations that I have available to retrieve mixed layer CAPE from and actually compare it to WoFS. Now, I want to point out, one, that WoFS over-forecast CAPE, and that the YSU scheme, because it predicted the lower CAPE of the three schemes, has the smallest biases on this day. Now, looking particularly at the soundings, and so on the left side here, we have a sounding with the observed temperature and dew point in the red and green lines, and then the dashed lines being the member temperatures, and the solid color lines being the dew point temperatures. And on the right-hand side, I have the vertical profiles of errors in temperature and dew point temperature. So to point out a few interesting aspects here, the first thing is that the PBL temperature is well enclosed by WoFS, and you're going to hear me use this phrasing quite a bit or not well enclosed, but WoFS is enclosing the observation, and so this means that WoFS at least has a chance of correctly forecasting what actually happened. So this is what we'd like to see. We like to see spread around the true value. The YSU scheme better predicts a drier planetary boundary layer, which is a bit anticipated based off of it being a non-local scheme with more aggressive mixing. And we can see here in a case that the drier YSU scheme was closer to the real observation. Another thing to point out here is that the YSU scheme predicts a weaker inversion layer that was more representative of the true environment. The non-local schemes, the MYJ and the MYNN scheme, predicted a stronger inversion layer than what was observed. Now looking at the near field 0106 observation, same images here, things to point out. One, there's more agreement among these members for the dew point and the inversion layer. And so the members sort of have converged to the appropriate solution. And the YSU scheme I also want to point out is predicting a weaker inversion layer. However, all of the members together do a good job of enclosing the observation. Okay. So now moving on to the kinematic variables. Here I have these same box plots. However, this is for 0 to 3 kilometer SRH. And all of the radiosondes made it above 3 kilometers. So fortunately, I was able to compare all of the 0 to 3 kilometer SRH values from these radiosonde observations. And one thing I probably should have mentioned when I was looking at the MLK plot is that the black horizontal line represents the observed value. And so we can see here that in the earlier observations, one actually being near field and far field, was that WoFS slightly over forecasts SRH early, but then later on, it actually under forecasts SRH. And so we can see that the environment, the SRH in the environment is increasing due to the presence of the supercell in the evening and other contributing factors. And WoFS does forecast that increase in SRH, but just not to the same extent that we see in the observations. And also I want to point out that none of these schemes consistently do better at predicting SRH than the other ones. So now we're going to look at, so I can see the screen. Now we're going to look at vertical errors of wind speeds. And so the panel A, these are these vertical errors. On the left, we have the zonal wind components. Here, the meridional V component of the wind. And in the solid black line is the observed wind, and the dashed black line would be the WoFS wind. And this is consistent through talk. And also here, it's difficult to distinguish the difference between these two in this particular observation, but we'll see that these differ a bit more in the future. The triangle represents the WoFS storm motion, and the circle represents the observed storm motion. And so here we have the ground relative photograph, and in C here we have the storm relative photograph, which will be especially helpful for diagnosing differences in SRH. So initially we see that WoFS overforecasts the V component of the wind in about 1 to 2 kilometers. And we can see that discrepancy here in the difference between that dashed and solid line. Now, whenever we rotate the winds to be storm relative, we can see that there's less observed streamwise vorticity in the storm relative winds, which is what's contributing to an overforecast of SRH. So it's essentially that reduced V component in the observation is what's causing WoFS to slightly overforecast the SRH, or at least a contributing factor. Now the near field 0106 observation, we can see that the photograph has enhanced, essentially the wind speeds have increased from the previous observation. I'll click back and forth here real quick so you guys can see that. And again, in a different sense, WoFS is now under forecasting the V component of the wind. And when we rotate that into a storm relative sense, we can see that that essentially results in stronger storm relative wind speeds in the observation versus the Warn-on-Forecast system. And this is what is at least one contributing factor to the under forecast of storm relative helicity. Okay. Now, moving on from radiosonde observations, I'm going to start talking about the Lidar observation, the one Lidar observation we collected on May 17th. And the cool thing about this is we started off in the far field, and as the storm approached, the Lidar clicked over to observing the near field, and so we captured this transition. So I'll take a moment to explain this graph real quick, as we will see this a few times in the talk. The solid line here is the observed rotational velocity. These lines here, we have the observed V component of the wind, observed U component of the wind, and in panels 2 and 3, we have the V component errors and the U component errors. Panel B, I have the WoFS and Lidar photographs overlain, which sometimes it's a little difficult to tell a difference between them. So in panels C and D, I've separated them so that C are the WoFS photographs and panel D are the Lidar photographs. And the lighter colors happened earlier on in the deployment, and so that means the darker colors are happening later on in the deployment. So one thing I want to point out about this is that the observed rotational velocity of the mesocyclone, which is essentially a proxy for how strong the supercell is, was relatively constant during this deployment. Now, we see that WoFS backs the wind, and so this is a counterclockwise rotation on a photograph. WoFS backs the wind in a similar fashion that we see in the observations. There is backing of the wind as the storm approaches. However, in the observations, the backing is stronger than what's seen in WoFS. And so we are seeing some storm modification here, just maybe not as strong as what we're seeing in the observation. Okay, so to summarize May 17th. WoFS did predict an environment favorable for supercells and reasonably accurate storm scale predictions of the McCook storm. The storm track errors were from about 0 to 40 kilometers, but the average error was about 14 kilometers to the southeast. WoFS did forecast storm modification, especially as time went on. The non-local scheme did perform marginally better than others at predicting the far field environment. Similar predictions among schemes in the near field. What we saw in the radiosondes was that WoFS over forecasts mixed layer CAPE and surface-based CAPE, and YSU has had the smallest errors as an impact of it predicting the smaller CAPE values. Now, WoFS over forecasts SRH in the earliest observations and then under forecasts SRH in the later observations. And the LiDAR, we saw that WoFS under forecasts backing of the wind as the storm approaches the LiDAR. It did forecast backing, just not to the same extent. Okay, now into the next case study. So this is from May 20th, which we may have all remembered that 24 hours of very stressful preparation for this day is SPC issued a high risk for tornadoes on this day. And we're going to be paying special attention to the supercell that produced the Mangum tornado. Here. And we have a radar image of that on the left and WoFS paintballs of that supercell in the middle. I'll overlay a circle here so you guys can see roughly the difference. Again, WoFS does predict storms in that location. However, there is, again, a southeastern bias in storm location. And it was a bit larger on May 20th than it was on May 17th, with about 20 kilometers southeastern bias. Now, the radiosonde observation, or one observation I'll be focusing on for May 20th, is this far field observation at 2052 UTC. Now, what we can see here, and again, this is the same image I showed you guys previously with the sounding on the left and the vertical profiles of errors of temperature and dew point on the right. So the PBL temperatures are a bit over forecasted by WoFS here. And also the WoFS under forecast the planetary boundary layer dew point, and we can see that it's a bit too dry in WoFS is essentially what we're seeing. Also, WoFS forecasts a weaker inversion layer than what is seen in the observation. I perhaps should have mentioned this, but none of the radiosondes actually made it up to the equilibrium level, and so I didn't have any observations available for mixed layer CAPE comparisons, but all of them did make it above 3 kilometers, and so we can look at SRH on this day. And the first thing that we notice here is that WoFS does a much better job on May 20th as far as this distribution of points encloses the observed value for every single observation made on May 20th. So good job for SRH, good job for WoFS on SRH on May 20th. And again, no scheme consistently predicts smaller errors here. Now, again, looking at that 2052 UTC radiosonde observation with the vertical profiles and error on the left and the ground relative and storm relative photographs here. And on this time, we can see that there is a bit of a difference in the storm motion vectors between WoFS and the observed. the observed storm motion is a bit faster than WoFS. However, the WoFS members, even in a storm relative sense, do enclose the observation, and so this is perhaps what contributes to smaller errors in SRH. And now we will be looking at the first LiDAR deployment on May 20th, which I believe is one of the longer ones of my case studies. These blue dots here. So again, we are capturing the transition between the far field and the near field with this LiDAR deployment. Okay. So again, the same plot, except the one specific difference here on May 20th versus May 17th is that the observed rotational velocity undergoes a strong drop here, a very rapid decrease in rotational velocity. And this happened because a supercell to its east merged with the target supercell, and there was some period of essentially reorganization of the updraft, which led to that drop in rotational velocity. Now, the really interesting thing here is WoFS backs the environment again, as the storm approaches the LiDAR, similar to what we saw on May 17th. However, the observed winds did not back, likely because of this drop in rotational velocity. Essentially, the storm lost some potential to modify the environment, and WoFS didn't exactly pick up on that and went ahead and backed the winds as though the storm was perhaps a similar strength as it had been previously. So this could have one particular reason why this could have happened is that WoFS maybe didn't forecast that merger of supercells resulting in a reorganization of the updrafts. And now we will look at the second LiDAR deployment, which are the red dots here. Click there and highlight that. And so this observation is, number one, near field the whole time. So this is a storm modified environment the entire time. And also the distance from the LiDAR to the storm is roughly the same throughout this deployment. And so really the orientation of the storm relative to the LiDAR is really what we're seeing as a difference here. So the rotational velocity of the storm does change a bit over this deployment, although it's not as drastic of a change as we saw in the last deployment. And WoFS forecast veering of the winds here, which is a little peculiar based off of the previous observations, but let me make some sense. The storm is essentially moving from a western direction relative to the LiDAR to a more northward orientation. And so this is what's dragging those winds to rotate clockwise on the photograph. And we do see that in the observation. So good job, WoFS. This is an example of perhaps one of the more accurate forecasts that WoFS issued as far as the storm modification of the wind field. Okay, so May 20th takeaways. So again, WoFS predicted environment favorable for supercells and reasonably accurate storm scale predictions of the Mangum storm. The storm track errors ranged from a similar range on May 17th from 0 to 40 kilometers, but about an average of 20 to 25 kilometers in southeastern direction. WoFS did forecast storm modification. However, there was no clear difference among PBL scheme forecasts. From the radiosondes, we saw that WoFS forecast SRH enclosed all 5 observations, so did a good job there. In the first deployment, WoFS backs the wind field more in the observation, likely because of that supercell merger that resulted in a drop in rotational velocity of the supercell. But in the second deployment, when the rotational velocity was roughly constant, we saw that WoFS does closely resemble the observed wind field. So that did a good job there. Now the third case study, May 23rd. First, I want to point out that the first target storm, you can see that these supercells were a bit in a line, and so we targeted the first one, observed it, and then moved off to the second one, moved off to the third one for this case study. So WoFS has had essentially a longer period of time to deal with target storm 1 and places that storm essentially correctly in the right spot. A lot of the members are overlapping each other right where the target storm truly existed. So it does a good job of forecasting the storm location of target storm 1. However, target storm 2 and 3, which if you're looking at the radar image on your left, looks distinguishable, but looking at the paintballs, it's not so easy to tell the difference between them. It sort of looks like one giant blob. And we actually saw the implication of this in the location errors as a function of time, where we see that we had relatively large large errors here before 2355, and then the errors drop at 2355, perhaps suggesting that WoFS was forecasting one giant storm, but then as it had more time to assimilate data, it was actually able to separate these updrafts. And so the UH objects initially were quite large, essentially conglomerating the second and the third storms together. But then once WoFS had an easier time, more time to assimilate data, WoFS was able to separate these two updrafts, and the UH objects were more representative of the second and third storm, and so we see those locations drop, the location errors drop. Okay. So for the radiosonde observations, I'm going to look at 3 of these here. 1 in the near field, 3 is in the far field, and same with 6 in the far field. There, so you guys can see that. Okay. Now, we did have 4 radiosondes that made it to the equilibrium level, so we have CAPE comparisons there. Again, that black horizontal line being the observed value, and the gray meaning that the radiosonde did not make it up high enough for CAPE comparisons. And what we see here again is that WoFS is over forecasting mixed layer CAPE, and because the YSU scheme is forecasting lower CAPE values, that results in smaller errors for the YSU scheme. Now, looking at the near field 2210 observation, we can point out here, 1, that the PBL temperatures are over forecasted, and this is one of the larger over forecasts of the observations that I looked at. However, the WoFS does enclose the planetary boundary layer dew point, so over forecasted temperature, but does a better job with the dew point. And WoFS forecasts a stronger inversion layer here than what we saw than what we saw in the observations. Looking to the far field 0105 or 0104 observation, the PBL temperature does enclose WoFS, so it does a bit better job here in the far field later on in the day. Excuse me. And WoFS still encloses the PBL dew point as well, so that does a good job there. And now WoFS encloses the inversion layer of the observation, and so it seems to be doing a bit better job here in the far field later on in the observing period. Okay. So now looking at 0 to 3 kilometer SRH, so back to kinematic variables, again, observed values on horizontal black line. Quick look, WoFS does a pretty good job again. Perhaps maybe the 0105 UTC observation where there's a slight under forecast, but that's the only one falling outside the 25 to 75 percentiles. And again, no scheme is consistently predicting smaller errors relative to the observations. Okay. Now back to the vertical profiles of errors of the U and B components of the wind and our ground relative and storm relative photographs. Here we can see that whenever we rotate the winds into a storm relative sense, that WoFS again encloses the observation, which again might contribute to smaller errors in SRH. Essentially, it is doing a good job of forecasting these winds. Now looking to the Lidar deployment, and these are kind of on top of each other in a storm relative sense, so I want you guys to pay special attention to the red X's here. So this is Lidar 2, which is near field the entire time. So first thing to point out again, that the rotational velocity is variable. It increases and then decreases. So this is a period of changing rotational velocity. And the WoFS forecasts it veers wind stronger than what was observed. But I do want to point out that the rough character of WoFS and the Lidar do resemble each other. It just seems like those WoFS photographs are shifted, or veered a bit more than the observation. Now, if you look to the V component and the U component of the errors in panel A2 and A3, the largest errors occur during the period when the rotational velocity is changing. And this is, I think, one of the more consistent themes of my research, is that whenever that rotational velocity is changing rapidly, we see these errors grow in the wind field. So May 23rd takeaways. WoFS again predicted an environment favorable for supercells and reasonable storm scale predictions, all 3 storms. We saw relatively large storm track errors here, greater than 50 kilometers before 2355, And then errors dropped to about 20 kilometers, similar to what we saw on May 17th and May 20th, likely due to WoFS accurately separating the updrafts of storms 2 and 3. Again, WoFS did predict storm modification of the wind field. There was no clear difference between PBL scheme forecasts. In the radiosonde observations, we saw that WoFS forecast of SRH enclosed 5 out of the 6 observations. And the latest observation, again, did fall outside of the distribution of those SRH values by about 80 meters squared per second squared. And for the Lidar in the second deployment, WoFS forecast stronger storm modification during a period of rapid increase in rotational velocity, resulting in errors of about 7 meters per second. Okay, so that concludes my case studies, and we're going to come back to the science questions that I wanted to address. So how closely is WoFS representing the inflow environment? All right, well, WoFS forecasts environments thermodynamically and kinematically supportive of supercells. So in general, WoFS is forecasting an environment that's going to produce some weather. However, WoFS over-forecasts mixed layer CAPE in every observation that we had available to compare for mixed layer CAPE. And WoFS under-forecasts SRH late on May 17th, but it forecasts pretty small errors, less than about 100 meters squared per second squared, in all observations on the 20th and 23rd. So did a pretty good job there. How accurate are WoFS storm scale predictions? Largely, the errors were smaller than 40 kilometers, maybe except for that May 23rd case where the UH objects were indistinguishable, and that resulted in larger errors. To what extent is WoFS predicting storm modification? Well, WoFS predicts storm modification with errors less than about 5 meters per second during periods of relatively constant rotational velocity, which we saw that on May 17th and in the second Lidar deployment on May 20th. However, the errors in the WoFS wind field increase during a period when the rotational velocity is changing rapidly, and that happened on the first Lidar deployment on May 20th and the second one on the 23rd. So back to this question of, can the ensemble mean be optimized by weighting members? Well, because WoFS over-forecasts mixed layer CAPE and YSU typically forecasts a lower mixed layer CAPE, perhaps weighting the YSU as far as that mixed layer CAPE forecast could result in a bit more accurate forecasts. And also, the YSU scheme did show to predict more reasonable inversion layers than the other schemes, particularly on May 17th. Now, no PBL scheme consistently forecasted smaller errors in SRH or storm location. Okay, so for future work, extend analysis to more cases. There are more cases available for TORUS2019, and TORUS actually plans on going out in 2021, hopefully. And so there will be more cases to analyze and perform this same analysis on. It'd be interesting to go ahead and calibrate WoFS a bit, change them, weight some members versus others and look at the forecasts and see if perhaps they're a bit more accurate or closer to the observed quantities. And also compare WoFS to observations made in different environments. This study was only done in American Great Plains, Supercells, springtime environments, and there are a wide variety. There's more environments that we could look at, especially hurricanes and derechos. Hurricanes is one that I would be particularly interested in because up until the precip started, you could get a very long time series of comparisons between observations and WoFS, and so that could be potentially a very interesting data set. Here are my references, and I'll conclude it there. Thank you for attending my talk, and I will take questions.
Okay, thank you. I think the best way to do this is to put the letter Q in the chat room, and if you have a question, and I'll go ahead and call on you then. Don't everyone type Q at once. Okay, Ted?
Yeah, I had to that's a nice talk. This isn't, well, I guess more of a comment that recently I saw some results when you're talking about the non-local versus the local schemes, that some work on the scale aware schemes suggests that just having a non-local component and turning that on and off as you get to higher resolution seems to work reasonably well. And since you're seeing slightly better results with the non-local scheme, I don't know if that suggests that you're at a coarse enough resolution for that, where that works better. I forget which way that goes, but anyway, that may fit in with those results.
No, certainly. And also, I mean, resolution is a factor, and also just the type of environment too. I mean, these observations were collected in, you know, environments are typically characterized by strong heating and really aggressive mixing. So it you know, it could make sense to have that non-local component essentially turn on whenever you have more aggressive mixing or finer resolution situations, like you said. Yeah, it'll be great to see how things like that play out for future case studies.
Well, I've got a question, I guess, sort of along those lines. So if you used well, I guess you basically found that you had, you know, a push in terms of storm relative velocity prediction between the different PBL schemes. No one scheme outperformed the others, but YSU seemed to do better for the Cape predictions. So is it worth having all of the different PBL schemes, or would it be better to just use YSU for all of the members? Or conversely to that, maybe a scale aware scheme like what Ted was talking about?
Right. Well, first, there's probably value in having the ensemble spread. So that, I mean, there would be one issue of if you had one particular PBL scheme may forecast, or you may end up having an ensemble that's not spread enough. And that could, I mean, essentially the point of an ensemble is having a whole bunch of possible situations in which you can back out probabilities of various things occurring. So if you say, well, you know, YSU did pretty well, so why don't we just only have YSU? Well, you sacrifice your ensemble spread in doing that. And so there's sort of a give and take there, that even if it does tend to perform a little bit better in some situations, you need to weigh that against that reduction in ensemble spread. So it's a difficult question to really get at, but I think it's really that interchange between perhaps something that's a bit more fitting for the environment with a non-local scheme, but you are getting that reduction in ensemble spread.
Yeah.
So just a quick administrative thing here. So if there are any other questions from the guests, go ahead and ask them now. I guess if Pat asked a question here, we may have just gone into the committee questions at this point. So if anyone else wants to ask a question, go ahead. Well, should we open up to the committee now, Pat, I guess?
Sounds good. So I guess everyone is welcome to stay on the line during the committee questioning. However, then we'll put you to a waiting room during the deliberation. So if there's no more questions, then I think the committee members will open up questions for you guys.
Before we do that, does Jordan need a break, or can we start that?
Thanks, Naoko. I'm probably okay. I'm okay. I can hop into it.
Okay.
Do you want to go first, Naoko?
Yeah, sure. Yeah, Jordan, thanks for a nice talk. This is obviously not an area of my expert, so I learned a lot. So maybe I'll just start with a question about when you talk about your error in the model ensemble relative to the observation. How do you know how much error is significant or not?
An excellent question. It's difficult to answer, because it's especially in a quantitative sense, because it depends on the situation and also sort of what you're hoping for the model to be doing at the time. For instance, we would hope that this model would eventually give probabilistic guidance on, say, tornado potential. So, or at least you know, a mesocyclone capable of producing a tornado. And in that case, you would anticipate very, you know, pretty strong wind speeds, you know, forecast by WoFS. So just for ballpark numbers, let's say, you know, 15 meters per second. So if it's off by, you know, a meter per second there, in an environment characterized by strong winds, maybe 1 meter per second isn't critical. However, if you're looking maybe at like a flash flooding situation that happened like last night, where the wind speeds are slow or smaller, 1 meter per second might be a little bit more meaningful there. So I do want to say, one, it's dependent on the environment, but two, it is really, for this analysis that I did, it was nice to just get a feel for roughly what is WoFS doing. Is it predicting storm modification at all? If it is doing so, you know, how is that a function of distance, things like that. But claiming, you know, that, let's say 1 meter per second is insignificant, 1 meter per second, yeah, it's insignificant, 2 meters per second is significant. I'm not really sure that differentiating between errors like that, it essentially might be too fine of a difference to be applicable to you know, research that I'm looking at for this.
Well, so given what you had, if you could add to what you've already done, do you think there's anything you can do to assess that kind of significance?
Certainly. So let's say in a world where it's a lot quicker to figure out where these storms are, let's say I had done 20 case studies. I could look at the significance of errors in a sense of just my distribution of errors that I found in those case studies. So let's say that I had one case study where I found mean errors of, again, like 1 meter per second, but I had other case studies where I found errors of 4 or 5 meters per second. So at least in the context of the case studies that I was looking at, you could come up with, you know, among all of these case studies, these errors are more significant than others, you know, relative to, in a relative case study sense.
Okay, I see what you're going. But I think there are things that you could still do given what you currently have. For example, for comparing your radiosonde profile to your model, you average over certain grid points. So there's still a variance within the locations that you average over. How does the error compare to the variance within the grid points that you averaged over? For example, that's one thing you could do. Maybe there are known errors to the observation or radiosonde measured quantity that I don't know. But if there is any, that's another maybe quantity that you could compare to.
Certainly, yeah. So if I'm talking about a ½ meter per second difference, but the radiosonde only measures observations, you know, with a resolution of 1 meter per second, then yeah, a ½ meter per second isn't exactly meaningful. No, so I definitely see what you're saying.
Yeah, I have other questions, but I'll let others ask.
I can hop in. So given some of the conversation we had and the more open questions, I wanted to follow up on some of those and follow up with some of the results you show throughout the thesis. And that is that out of the schemes, YSU often has kind of the lowest error. And this, you say, is confirming of some of the previous studies on systems like WoFS. But from a process standpoint, is YSU actually representing anything more physical representation of processes, or is it just more often warm and dry, which in these scenarios happens to improve the forecast?
Good question. Well, the particular environment I'm looking at, I would intuitively think is influenced by stronger mixing, stronger surface heating than we could see in other environments. And so, you know, there's probably going to be very, very strong mixing, which is going to force counter gradient fluxes. You know, if you have a warm plume of air that goes up, that's, you know, just mass conservation. It's going to shove air down somewhere else. And maybe a non-local scheme may not have as easy of a time representing that. So is it just representing warmer and drier environments? Probably, and I mean, systematically it does do that, but I think that does come back to the physical process of it has stronger, more aggressive mixing. And so there is some physical support for that idea. And so, yeah, I do think there is some physical process there that is backing up those differences.
So, well, actually, Naoko stole my first question. So, but the second question I was going to, or another question I was going to ask is, so when you were showing all these difference plots in the SQTs, in the temperature and the dew points, you focused a lot on the very lower levels, but I didn't really see you much focus on the big differences that are happening above, like in the free troposphere. And so I'm wondering if you have some, what comments do you have about that, and how might that also be impacting some of the errors that you're seeing? Besides CAPE, I know CAPE can be erroneous because of that, but perhaps other things to do with the environment. What are some of the implications for the errors in the free troposphere?
Certainly. So just to motivate why I was looking particularly in the lower levels, I mean, the differences of these schemes are at least thought to matter where this turbulent mixing is happening. So that was sort of my initial motivation is, you know, if the difference is the turbulence, let me look where the turbulence is. And so really above the PBL, I focus less on those. Now, those differences, actually, let me say this too. As far as the air that these supercells are inhaling, it's coming largely from the lower levels. And so it's characterizing particularly the kinematic environment in say the lowest 3 kilometers is critically important for the evolution of a supercell in general. And also there have been studies that have looked at, you know, tornadic versus non-tornadic cases, and certainly upper levels are not unimportant, but it's just that there's more importance you know, focused on those lower levels. As far as, you know, if we are to look at the upper levels, there were some things that were interesting differences that we did talk about through the course of my research, but I just decided not to focus on for this talk. Specifically, one of them is where clouds are being resolved in WoFS versus the observation, because we can see, you know, where the profile saturates in the radiosonde observations, for example. And we could compare that to where are clouds, you know, being predicted in WoFS, and could that have implications on, say, solar heating at the surface, something like that. I think, though, I didn't analyze that in a framework of which PBL schemes are doing better up high, simply because I didn't really anticipate that there would be a huge difference between them. That's not to say that there aren't differences that could be important. It's just not where I was really focusing.
Yeah, I just noticed that in a lot of your plots, it seems like that in the models, it's much drier than what the observed dew point is. Or sorry, more, maybe in most cases a little bit more moist. So you had a lot of positive errors, right? Is that, I think the ones that I looked at, you had a lot of positive errors. Is that right? Did I get that, the sign right?
Yeah, there are some regions where, yeah, like just looking on May 17th. Actually, I think my screen is still shared, so I think you guys.
Yeah, I can see.
Okay, so for example, on this one here, we do have maybe a little bit more negative errors in dew point, but there is this strong essentially surge in positive errors here. Yeah, I know, and that does look like from essentially there's this dry layer in the observation that WoFS apparently is doing less of. It's not doing a great job of resolving. And also just to point out between the difference, these two observations, one in the far field, one near field, one's taken earlier than the other. This dry layer, there's a dry layer that exists at about like 700 or 650 millibars that WoFS does a good job of predicting. But in the later observation, either one, this dry layer has moved up in pressure, or there's some other mechanism, generating this dry layer or at least causing it to be higher up. And it looks like WoFS has a harder time there. Yeah, no, that was certainly a feature, and actually I can find other ones where, at least I think on May 20th, it was caused more so where the clouds are existing. That were issues, and actually this may be an example of, I guess there are some positive errors here in that dry slot. Yeah, so it does seem wherever we have these really dry regions that WoFS has a tendency to maybe not make it as dry. So, or maybe I could phrase that more generally, that in extreme changes of dew point temperature, WoFS is a bit less extreme. So that kind of results in some errors there.
Jordan, I have a question. Oh, sorry, was that you, Mike? Okay, if you went back to the May 17th sounding that we were just looking at, where you're looking at the situation where there was WoFS members that were under predicting the extent of a dry layer. Yeah, this one. And I think you mentioned something about whether you didn't know whether or not that arose through, whether that's something that's in the broader environment or if that's something specific to the WoFS configuration. So I wonder if you could just speculate a little bit more based on what you see in the plot as to whether you think, which one you think is more likely.
Well, I mean, my inclination, just because off the extreme drop in dew point, I mean, it is very, very dry. That may be caused, and there might be a slight uptick in temperature, could be from some heating caused, wherever the radiosonde was traveling through. There could have been some heating caused by the storm, maybe some latent heating that resulted in a higher temperatures, which may in lower dew point temperatures. Although saying that drier air being caused by the presence of a supercell seems awkward or backwards, really. But it seems like there would be something physical causing that really dry area that WoFS is having a harder time with.
Right, and I was looking more so for the errors in WoFS. So looking at the individual member plots, does it look like you're actually seeing the influence of basically the PBL characterization in representing this mid-level dew point error?
Could be. I mean, it does look like there are some MYJ schemes and some. Actually, it looks like there's a few, or at least one or two of each of the three types of PBL schemes that do forecast that really dry area. It does seem like maybe the MYNN and the YSU schemes, for some reason, some of them don't forecast near as dry of a region. But it is interesting to point out that there's a wider spread in the ensemble in relation to that dry region. Where we see it get very dry, you see the ensemble kind of spread apart and lose some agreement there. So it seems like there could be some of those members were picking up on the dry area and others weren't. So maybe this could be, maybe the storms themselves looked a little bit different in some members. Some of them maybe had more representative storms, and others didn't. Perhaps that difference is resulting in that spread spread in the ensemble. Physically, what would be driving that, I admit, I'm not exactly sure, but it does seem to be, you know, wherever you have that dry region, you're having a large, you know, you have larger errors within the model.
Yeah, and I think that's a good thing, because you'd want, where there's a more extreme change, to have a larger spread there. And I thought what caught my eye was that the MYN and MYJ are so different. And so you have, you know, the two local schemes, and you actually have a really large difference between the two groups, where MYJ is, you know, YSU is kind of in between, but normally the MYJ and the MYNs are pretty clustered. So I don't know why that might be. It was just something that I thought was interesting.
Certainly. Yeah, and it's probably something, I mean, because you have some, you know, you have your local schemes doing well and other local schemes not forecasting that well, it's probably something other than the scheme differences resulting in that. Although I'm not sure what it would be.
Well, while we're on soundings, can you go to the May, I think it was the 23rd, the very first sounding you showed?
That guy there?
Yeah. So can you speculate why the errors were so bad in the PBL there in temperature?
Oh yeah, the surface.
And even aloft too.
Right. So just like rapidly here. Yep. So clicking between these, you can see that the observation doesn't change a whole heck of a lot. And it's really that WoFS is changing. That's what's resulting in those errors. So, and this is the near field, this is the far field. So the near field temperatures are warmer. Now that, could be clouds, honestly, because the, you know, if we're looking here in the near field, there, and this is something that for Naoko and Jason that I've talked about with my advisors a little bit, is that you can see that the profile saturates here at about 300 hectopascals, and WoFS saturates higher than that, and it doesn't exactly saturate, and this is a question of saturation with respect to ice or water, but usually, I mean, the way that we're looking at this here is that if these lines are you know, paralleling each other and they're relatively close, that's sort of where we're looking at, like WoFS is going to be forecasting an anvil in this case because it's so high up in the air. And we confirm this with satellite imagery. But here in the near field, one, the observed cloud layer is much lower than we saw in WoFS, and there's actually quite a bit of spread in the depth of that anvil in WoFS. Some of these members don't even, you know, don't really forecast or really forecast much of an anvil at all here. Whereas in the near field, the entire profile, here in the far field, the entire profile is much more moist, and so I would probably assume that one, WoFS, you know, as an ensemble is predicting this anvil in this location, but it's also a lot thick. You know, the anvil itself is a lot thicker here. And so what may be the issue is that here in this near field observation where, you know, it's drier, maybe there's an anvil, maybe some members have it, others don't. WoFS thinks that the sun's beaming on the ground here. And so if that's not actually happening, then that could result in large surface temperature errors there. So I think my first inclination would be to blame it on the clouds, essentially.
Yeah, it's interesting. If that's the case, I mean, you'd expect to see shallower PBL there on moisture, or moisture cooler PBL, if the mixing was a lot less in reality than what WoFS was representing. But then you go aloft and you actually see what looks like mixing extending pretty high up to 700 in that observed profile, which is kind of interesting.
And if I can make a comment on that, it could be, I mean, mixing can be driven by other things than just solar heating, right? I mean, you could have terrain impacts, you know, if the wind speeds are stronger, you could have frictional impacts that could help out with that mixing. So even in an environment where it's, you know, it's really cloudy and maybe solar heating isn't driving a lot of that turbulence, a difference could be at least stronger wind speeds, different terrain, which I believe that May 23rd was out in the panhandle of Texas, which can be very flat, but there are also some regions of valleys and such that could help generate some frictional turbulence that could be assisting that mixing.
Well, or it could just be a large-scale error from the background that was provided to the WoFS too. That, since all the times we've seen this, I never really noticed that till you showed it here today. Yeah, not real sure what to make of that, but.
I have a question kind of following up on all this discussion about how to interpret your results in a physical meaning way. Mm-hmm. I think to do that, it's kind of important to go back to your second question. Either on, I think you had it summarized. Yeah, so how accurate are WoF, you call it WoFS, storm scale predictions? So you only talked about location, which is just based on a centroid. You could have the same centroid, but a very different storm, right? So have you thought about other aspects or properties of the storm, predicted storms, that could be important to interpreting your results here?
Certainly. I mean, the first thing to think of would be reflectivity. You could, I used updraft helicity because whenever I looked and tried to find a location for the observed storm, I picked its location by essentially pinpointing the velocity couplet. And so I, thought the updraft helicity would be, the proxy for that in the model world. Although I could have done it based off of reflectivity centroids. So it's still a centroid, but using a different variable. And
I think I was kind of curious to learning more about was how did the models predict intensity, size, timing of the life cycle, and orientation? I think that could all influence, kind of interpretation of your results.
Yeah, absolutely.
Yeah, because I thought like the interesting part of this research was, I thought if I understood it correctly, you were trying to get after this interaction between the environment and then the storm, right? And then you kind of had a lot of focus and interpretation on how well the model did on kind of near storm or far field environment. But then I was kind of looking forward, you bridging that back to the storm prediction, which is the ultimate goal of the WoFS, right? To improve the prediction of the storm itself. So I think I'm looking forward to bridge back to how your result, can feed back to understanding the forecast skills of the storm itself.
Right, absolutely. And I think the May 20th Lidar deployment is a really good example of that, where we saw that drop in mesocyclone strength for the observed, because you may have caught it, but in my slide I basically said WoFS could have missed that supercell merger, and that could have been a reason. And the reason why I don't know that is I didn't look at the strength of the updrafts in WoFS. I suppose that I could have looked at the UH object that I grabbed. Instead of just calculating the centroid, I could have calculated, say, the average UH value across those grid points, and that would have given me a feel for are the storms of WoFS stronger, weaker? Is there a large spread? And then relating that back to the environmental differences. So certainly that is something that would be helpful to better understand the differences that I'm showing here.
Yeah, I think it would be nice to add to the end of your thesis, like based on, well, if your focus is on the difference based on the PBL scheme, did the PBL scheme with better forecast scale of environment, did that ultimately lead to better forecast of the storm itself or not? I think that would be like a nice concluding thing to add to your thesis.
Definitely, and actually the paper that I referenced that did look at systematic differences of PVL schemes saw that the YSU scheme more accurately predicted the environmental variables, but at the same time the storms were weaker in the YSU scheme, and so it's sort of on one hand it's maybe it's better predicting the numbers you would look at as a forecaster to get a feel for the potential of environment, but at the same time forecasting storms that are too weak. So no, certainly, I think that would really help analysis.
I want to just jump in real quick to kind of follow up on Naoko's point, or points she made. Another additional thing is that I much preferred from the way you presented this material, this idea of these questions and answering these questions, because that did not come across in the thesis, that these were your central questions that you were asking and that you were answering. And so all the analysis and everything was fine, but I never got this central, like, what are my hypotheses? What are my questions? And what did my analysis tell me about it? And how does this, and sort of then to build on like Naoko's point, how does this extend into a more kind of general applicability of the results? I think that, I mean, for me in the written part, it was missing that sort of framework for me, at least. I think it came across much better here in the presentation, and I like how it was laid out here because it helped to frame everything. So I don't know, I think it would be nice to have this sort of framework laid out.
No, I appreciate that, and also I mean I feel like that comment like that is sort of the value of having folks on my committee that are not exactly severe weather people, because when I spend all of my time talking with Pat, Mike, and Liz, some of these things are I don't think to really to explicitly state these hypotheses, because they're sort of just like general questions to us that we're thinking about a lot. So certainly I'll in the next revision I'll aim to do a better job of really focusing on the questions I'm trying to answer here.
Yeah, I had very similar comments in the thesis that when I read it through this time, and I highlighted something similar, that kind of story arc is missing. But kind of related to what Naoko was getting at a few minutes ago, and also when you're ending the thesis, you're talking about potentially in future work looking at these lagged forecasts. And I was wondering if you'd spent some time thinking about that, and you can think about some sort of parameter or proxy that we could actually look at in the WoFS output that would act as a measure of that storm modification. When you're doing your analysis, you're showing it in several different ways here, but now that you know this, is there something we could look for in the WoFS output that could act as a proxy for that?
Certainly. I mean, I'm initially drawn to mixed layer CAPE and SRH simply because they're nice, easy numbers to look at, and lagging them, it would, if I showed that, if I compare these observations to WoFS forecasts that happen actually 10 minutes after the observation, are those SRH, ML CAPE and SRH errors smaller, across the case studies, certainly. Now, I could probably do the same analysis with just errors in the wind field, or errors, in temperature and dew point as well, considering that those happen at, different vertical levels. It adds a dimension to it, but I could do that as well. Lag those variables and take a look at, is WoFS forecasting the temperature better actually 10 minutes after the observation, as opposed to at the same time. I think I would start out with mixed layer CAPE and SRH just for a first run through analysis, but I could do that with other variables as well.
Well, kind of along those lines, thinking about, what physically drives a supercells modification of the surrounding, certainly wind field, also thermodynamic field. I was wondering about, maybe revisiting that question in terms of, what do you expect to change the most in proximity to a supercell?
Between thermodynamic and kinematic variables, or
Or just
like
about, basically, yeah, any environmental variable you can think of.
I mean, I have an inclination to say, the wind field is the main thing that I'd expect to see the difference in, because there are several contributing factors that could increase the wind field. The pressure perturbations based off of rotating updraft, latent heat release, also leading to lower pressures, increasing the wind field. And also with, say, something like if you have precipitation falling into the inflow, that may or may not happen depending on the type of supercell you're looking at, like particularly with like low precipitation supercells. The thermodynamic response may not be as strong as the kinematic response. I mean, essentially, if you have a supercell, you definitely have a rotating updraft. And so that kind of seems like that first, if we're talking about storm modification, the first thing I think of is the changes in the wind field. That's given a sense. Whereas precipitation is a bit more variable, and also cloud cover, like anvil shading, is a bit more variable. I would think.
I agree. And based on that, I wanted to just, if you could go back and look at the second LiDAR deployment on May 20th, when WoFS did a generally good job, and compare that to the near field LiDAR deployment on May 17th. And if you could just remark on, what are some of the differences in the SRH between these two? I think and actually you could even bring the soundings in on this one too, if you want to look at the box plots with the SRH errors out between May 20th and May 17th. Okay. So there's May 17th, right? And there's May 20th. Or wait.
Yeah, May 20th. So, I mean, we're looking at SRH values in the vicinity of like 200 to 400, where May 17th, we actually get a bit above 400. So perhaps, especially in this near field environment one, that, these SRH values look a bit stronger than.
Wait, is that May 7th? That's not May 17th though, is it? That's May 20th.
Oops, sorry.
No worries.
Oh, there we go. Yeah, okay. Okay, so similar values.
Look at the observations for May 17th for the 0 to 3 SRH. Like, what are the max SRH values?
Oh yeah, okay, a lot stronger. Yeah, okay, I see that. So yeah, we have, the 0105 is like almost, it's like 700 meters squared per second squared. We've got almost 600, 500-ish. Whereas on May 20th, they are quite a bit lower, right? Especially in these near field ones. So it does seem like maybe that McCook supercell was a bit stronger. Well, actually, let me look at rotational velocity real quick. So observed rotational velocity is about 40 meters per second, a little bit under it. The second LiDAR deployment here it approaches that later on, although it's a bit lower than that. So it does seem like that whenever the meso really gets going, we do see values about 40 meters per second in the rotational velocity, and most of the deployments, except for that drop there, and on May 17th, it's a bit more consistent.
Yeah.
But it looks like the meso is roughly the same strength between the McCook and the Mangum supercells in a general sense.
So then what would be the reason for seeing this, a dramatic intensification of the observed storm relative velocity on May 17th that's not present on May 20th if the observed rotational velocity is roughly similar?
Well, it could, so it could be ambient environment, like just the the environment before the supercell formed on May 17th could have included more streamwise vorticity than the environment in the May 20th. However, that being said, I recall the photographs on May 20th being quite large and having very strong wind speeds on that day.
Mm-hmm. Well, and just one last question: like when you're making a forecast, during TORUS, if you're going to go out chase or deploy, and you look at the 0 to 3 kilometer storm felicity, what would you consider to be like a large value? What would you look at?
Yeah, a lot. I mean, I guess anything I guess above 300 is interesting. Really, even anything above 200 is pretty interesting.
Exactly.
A large value, I'd say like 300 to 400 maybe.
So when you see something like 600 or 700 in that, what's that telling you about the environment?
It is extremely, that is definitely like upper percentiles as far as environmental SRH. So it's the environment near the Cook supercell certainly was definitely stronger. Certainly, and actually, I may want to mention one thing real quick. Those observations could have to do with storm motion, because I remember on May 20th the storm motions were very strong, and the storms are moving through their environment very quickly. And so, like, let's say for instance you had a stationary supercell, it could just sit there and work and work and work on the same environment and really ramp up the SRH in the environment, maybe more so than a storm that's moving through more quickly.
Well, keep in mind that the SR part of storm relative felicity, so you're always going to be correcting for the storm motion. But yeah, a supercell with more deviant motion is able to realize greater effective storm relative felicity.
No, certainly. So, right. No, I guess, yeah. Because I guess what I'm saying is there's sort of like an accumulation of the impact of the storm modification in a sense. If you have a supercell sitting there for hours and hours and hours on end and really ramping up the environment, I could see how that situation could result in larger SRH values, even if the storm motions were similar, versus a supercell that of similar strength that simply hasn't existed for as long, or at least not in that environment. So it's a sense of like how long has the supercell been modifying its environment at a given strength.
I agree, and I think one last part of this question, and that's based on what you just said. So how would you go about measuring, how long has the supercell been modifying its environment, or what would be maybe an alternative measure of a supercell's ability to modify its environment than just looking at the rotational velocity?
It's history in a sense. If the supercell's there longer, definitely.
Well, I was thinking, like, if you think about what is the pressure response in the inflow of a supercell, what's driving that?
Aside from the rotating updraft, I mean, you have latent heat release. So I mean, like a high precipitation supercell, could have a stronger, pressure perturbation than one that's not.
I'm thinking it's mainly rotationally driven, though. So when you think about, like,
Right.
what is the net impact of rotationally driven pressure perturbations from a mesocyclone? It's tricky, but what's something else besides just the rotational velocity that you get from radar that could be impacting basically the pressure gradient forcing?
It could be the number one, the cross-sectional size. I mean, like how big it is, and also the depth of that rotational velocity. So, keep in mind whenever when I'm saying here's rotational velocity of the mesocyclone, I'm only able to actually calculate that at the height of the radar beam. So there could be some variation in height of the rotational velocity as well, aside from just size.
Exactly. No, I think that's something that's worth looking at a little bit more in depth. Not for the thesis, but for the paper, are some alternative ways of defining the strength of the observed supercell mesocyclones.
Yeah, definitely. I'm not sure how I'd get around the height issue, but certainly like the size of the updraft in a horizontal sense definitely could be something to look at. with the data that I have.
Yeah, I agree.
So I'd like to ask one observation question since we've been talking a lot about WoFS itself. So now that you've done a lot of this work and you've gotten to look at these data in interesting ways, do you have any modifications that you would suggest to a deployment strategy like TORUS uses to better be able to accomplish the goals of a study like yours?
Not to get on anybody's case, but like maybe not like the observational, because what we did in TORUS is, you know, we observed the supercell with, I believe, 3 different ground-based radars that were just a part of the TORUS team, not even counting the WSRs. You know, we had the 2 KAs and the NOAA radar. So simply just having that information at my disposal would be great for an analysis like this, especially if we're talking about, you know, looking at the mesocyclone at different heights. You know, maybe that could provide that. Maybe the KAs could help with like the low-level meso. The NOAA radar a bit higher up, you know, maybe just a different beam height, what the WSR was at. Now, specifically from like an observational standpoint, like what could we have done in TORUS to better, you know, observe the supercell, or at least like, you know, provide me with data that would work. I'm not even sure, because we had the P3 Orion out there too, so it's like we even had radar observations from above, which, you know, it feels like more than I could ask for right there. I guess just having that observational data available to me in, you know, in a time appropriate sense is really the only thing that I could come up with, because we really, you know, we did I don't want to toot our own horn, but did a great job observing the supercell. You know, like multiple different platforms. I can't even think of anything else we could have done.
What about thermodynamics? Because we don't really have any. So you showed these really nice LiDAR plots, right? That we get these time series of kinematics, but what about thermodynamics?
Oh, certainly. Setting up weather stations, actually, now that you say that, like we do for hurricanes, where we set up pods, and that collects time series of like surface temperature, pressure, and humidity, and things like that. Actually, that is one thing. Setting up pods could be a thing that we could have done. You know, go out into a location that we think could be favorable for supercells, and just deploying pods the morning of in various locations could provide time series data that would be good to have. Yeah, and also I think something that had been done in the past was like coordinated balloon launches. That could also have been a thing, because all of my radiosonde observations are collected in different locations at different times, and so I don't really have a sense of here's what the near field and the far field environments looked like at the exact same time. We did have, you know, we had 3 vehicles that I can think of off the top of my head that were capable of releasing radiosondes, but I don't think we had any coordination amongst them. So perhaps more coordination there to pair up those data sets. And also, you know, I like windsondes could also be a thing to bring up here. We did have windsondes, but having coordinated windsonde launches, or simply just having more of them, could also have helped providing more data.
Okay. I would like 12 more LiDAR vehicles, Liz, to put out in the inflow. That would be nice. But on that topic, Pat kind of stole my thunder on the May 20th case. But one thing you didn't mention that I think was actually probably the most important thing for why we're seeing differences there in those 2 cases. Can you go back to just the deployment plots?
This guy here.
So that's the 17th, right? And then
It's 17. So this
is what's different between those 2?
From LiDAR or radiosonde, or both?
The LiDAR.
Well, the first thing I noticed is the LiDAR is oriented more toward the north in the storm relative sense. Especially, obviously the second LiDAR deployment is really to the east, the southeast. And so the storm modification that you see in the photograph is going to be dependent on the orientation of the storm relative to the LiDAR, right? Because the storm creates a low pressure, draws the wind field in that direction. So, and actually I think there was, I think it is that second deployment where we see veering of the winds actually. Except, in the May 17th, we saw a backing of the winds. Both are storm modification. And the difference is the orientation of that storm relative to the LiDAR. If the storm's on like the southwest side, we see more backing. If the storm's north of it, you see more veering as the storm starts to go away. So, definitely, the orientation is definitely relevant.
So, you have evidence here that the modification to the wind field is a function of azimuth from the updraft and storm motion. So with as far away as the LiDAR was on May 20th, and you can blame me for that. I didn't position it quite right on that day, but so even though you have it going into the orange here, I mean, the near field doesn't magically start at 40 kilometers all the time for every storm. So that's a function of storm longevity, like you already said, storm strength, background environment, a lot of things. So hence why I would like to have 12 LiDARs spaced out in a network out there to measure this.
Yeah, no, definitely. And the 40 kilometers is certainly variable, right? Because if you have a really weak supercell, maybe it's 20, 30 kilometers, something like that. If it's extremely strong, maybe 50 or 60. Right.
Yeah.
Hey, Jordan, very small detail that I didn't notice until this presentation, but on the slide, the table you have of the LiDAR 1 deployment has too many near field coloring bars in it, right? It looks like half of the colors in the near field.
It definitely does. No, you're definitely right, because there's only 4 observations in the near field, and I've got like half of them lit up.
Yeah, so just a small detail to correct.
Yeah, and I imagine that's in the paper too, because I use the same figure, so I'll make sure to correct that.
Yeah, so actually it hit me. Go back to the sounding that I asked about earlier, the May 23rd, where the PBL temperatures were too cool. Yeah, looking aloft there. There is one other thing that a storm can do to inflowing air that I don't think you talked about here, that might create that profile that you see in observations there. Can you think of what that might be?
As far as the fact that the PBL temperatures are cooler, what's causing that cooling?
No, sorry. Actually, I was thinking about above the PBL there, from 750 to 650 millibars there.
That little dent right there?
Or just that layer in between. What the you have where it's much more saturated in the observation, much cooler than in the model, or even just leave the model out of it. Just what might create that profile there.
This right here?
Yeah, that layer in there that's humid, relatively humid above the PBL and below the dry layer there.
My gut reflex is evaporational cooling. I mean, whenever you have supercell and you get liquid water and then it evaporates on the outside of the storm, it cools the surrounding air.
That's one of the 2 possibilities for creating that. What might be the other one? Storm creates low pressure, and low pressure is not really at the surface too. It extends in a column. So what might that do to the air?
Expand it. I mean, if the air expands, it'll cool.
Well, so we've been talking about air, horizontal winds here.
Oh, yeah, if you have air that's moving upwards, it's evaporational. I mean, it's cooling adiabatically as it goes up.
Yeah.
So that could be it.
Yeah, that might actually be a sign of strong mesoscale lift that was happening in the environment there that wasn't in WoFS. And it's in the near field, so it may actually be the storm that's inducing lifting there. And that's actually a signal that we saw in impacts as well.
It's a great argument for time series thermodynamic profilers.
There you go. It all ties together. See something, I actually never saw that. All the times we looked at these profiles, it never really clicked until I saw it here. There's always something new to see when you look at this.
Yeah, no, I definitely saw that. I wasn't sure what it was. I mean, the first wrong idea that popped in my head was like there's some weird second inversion at like 600 hectopascals, and I just looked kind of.
Yeah, no, it can be hard to separate the effects from evaporation from the anvil and from the effects of the background lift. And just observations of, precip and radar observations can help with that too. I think I'm done.
Yeah, I've asked everything I was going to ask.
I think I'm all set as well.
I'm here.
Same here.
So if everyone's ready, I'm going to, Jordan, anyone else on the call, I'll put you in the waiting room and then the committee can stay on.